Hello, everyone. My name is Mike Alperin. Today we're going to do an informal session on machine learning in manufacturing. We'll cover just kind of give you a taste of some of the work that we've been doing in this area. We'll be covering everything from kind of data mining, root cause analysis to real-time processing. My name is Mike Alperin. I'm an industry consultant at TIBCO, focusing mostly on manufacturing, and I work very closely with the data science team. And Kai, do you want to give a quick introduction?
Sure, sure. Hey, and my name is Kai Wenner. I'm based in Germany, and I'm a technology evangelist, and that means I also take a look at many different hot topics. And machine learning right now is, of course, one of them, and how we can leverage that in TIBCO. And that will be one of the main topics today. And maybe before we begin, for you also the information, this session is recorded, so you can also watch it afterwards again or share it with colleagues afterwards. And with that, I think, Mike, we can begin.
So I'll quickly review the agenda. We're going to start out and do kind of a quick kind of high-level introduction to machine learning. You know, what is it? We'll focus a little bit on some of the algorithms that we're going to be demonstrating later on and why it's useful and applicable for certain use cases. Focus a little bit on how we're using it in manufacturing. Then we'll review some of the high-level kind of methodology that we use to essentially tie together some of the data mining and the real-time and predictive work. Then I'll do a demo that focuses really on data mining or root cause analysis in manufacturing, and Kai will then do a demo that focuses on real-time processing of data. So with that, we'll begin the introduction to machine learning.
Yeah, and with that, let's begin from a very high level so that we all have the same understanding before we focus on manufacturing afterwards. If you take a look at the picture here, that's basically really explaining what machine learning is. And it is really that it allows computers to find hidden insights without being explicitly programmed. And that's really the key here. So what you basically know from programming languages, and when you write some algorithms or applications, then usually you write expressions and loops like if, else, or for and while, and all these kind of things. So you explicitly tell the computer what he has to do. And machine learning is really different because here the computer learns by himself, because we're talking about big data and so many different structures and information. And here in these use cases, like you will see later, you cannot program everything for the computer. He has to learn. And that's why this is getting such a hot topic today with all this big data and Internet of Things and all this kind of stuff. And with that, let's take a look at a few general use cases first. So really from the real world, and the first example is spam detection. We know this for 20 years or so now, and here really you know that from your email mailbox, the machine has to learn what kind of email in your inbox is spam and what is not spam. And it's not very easy to program that with the programming languages and with if, else, and while loops and so on. So you can't tell your program if it is spam. The computer has to learn that, because the spam, as you know it, and the text is changing every day and every minute, and so you cannot write a rule for every single spam mail, right? And therefore, machine learning is used to do that in the background. So the second example is what you also do every day in your daily life is using a search engine to do search queries. And the search engine in the background on the servers also uses and leverages machine learning to give you the best search results. So maybe 10 or 15 years ago when you searched at Google, then everybody got the same result and the same advertising. So this changed, of course. So in the meantime, Google gives you the personalized, context-based information you want to see for both, for the search results, but also for the product recommendations and what advertisements Google is showing you. So that's also key here, and machine learning is doing that under the hood, because otherwise you can't do that for millions of people in a personalized way. So the machine has to learn to do that for your program. And the third example, and that's really even more sophisticated, and that's just starting. So some people also call that deep learning because it's much more compute intensive, and here you're really analyzing pictures and you're analyzing videos, and that's so much more powerful because when you take a look at your Facebook videos and photos you upload, or other services like from Amazon and Google where you can upload your pictures for free. And of course, it is not free because therefore you give all your information to them. And in the meantime, it's really already possible that Facebook, for example, analyzes all your pictures with machine learning algorithms in the back. They can detect friends of you, they can detect the locations where you are at the moment and what product to use. So what kind of beer do you drink, or what food do you eat? And based on that, they can give you better recommendations, in the end, better advertising. And so that's really a huge story about machine learning and how this is used in your daily lives. And now, of course, it continues, because now machine learning, every enterprise is beginning to leverage it. And that's basically what we begin with today, and what we want to show you today specifically for manufacturing, how you can leverage machine learning in the same case as these tech giants like Google and Facebook do for years now. And therefore, let's now go over to some more technical details, and Mike will explain you the different types of machine learning available.
So we've, in our work, we've focused on three kind of main types of machine learning. They're called kind of supervised, unsupervised, and the third one I'll call optimization. So supervised learning is, where you define the problem, and so the algorithm is going to then solve some kind of a known, well-defined problem. An example of that in manufacturing would be you have some kind of a problem, and, for example, it's manufacturing defects or yield or something like that, and you want to know what are the factors that are driving that, and maybe then you want to build a model to kind of predict that kind of, those kind of failures in the future. So the types of algorithms we've been using there are for the most part based on decision trees and random forest. Gradient boosting machines are kind of variations on that, and I will go into that more in the next few slides. And this is really where we're going to be focusing this webinar on, is some of the supervised machine learning cases. Other use cases that we're not going to cover now, but we could kind of do in future webinars, are unsupervised learning. So that's really where you just throw a bunch of data at the algorithm, and you let it identify kind of new patterns, maybe detect anomalies or outliers. So there you're asking questions like, is there some kind of a new failure mode or pattern emerging that I had never seen before? And we use techniques like clustering, principal components, neural networks, and support vector machines for that. The third type of algorithm that we've been working with are things that are really optimization algorithms. They support decision making. One area that's especially fruitful in manufacturing is figuring out what's the optimum scheduling of operators or equipment maintenance, and these may be problems that are highly constrained. You need to know what's the schedule of each person and what are their preferences and what machines are they qualified on. So you have a lot of constraints there, and then there's kind of an optimum solution that can be provided. So those types of algorithms are genetic algorithms. At least those are the ones we've been working with. So if we look a little bit more at decision tree, I said we're going to be focusing mostly on decision trees for the rest of this webinar. Here's a very simple example of a decision tree, and it's based on data that indicates what would be the survival rate of passengers on the Titanic. So if we look at the very top here, this was the most important kind of predictor, is what was the, what was the gender of the person, male or female. And if they were female, they had a 73% survival rate. So that's pretty simple. As we look down the left-hand side of this tree, things get a little bit more complicated. If it was a male and they were less than, 9.5 years old, then there was a very high percent, chance that they died, so they only had a 17% survival rate. And then as we kind of go down the right-hand side here, the highest survival rate for males is that they were older than 9.5. They had a family size over 2.5, and then they had a very high survival rate. So that's just kind of a simple example of a decision tree, and this is the type of technology that we're basically working with from here on out. So just kind of a quick comparison, if we look at classical statistics, we're usually kind of fitting parameters to some kind of a well-defined model. Is it a quadratic model or an exponential model? And really one of the issues with that is that your choice of the model then determines, what kind of results you're going to get. If you don't know, you may not know enough about a problem to really know which model you're going to use. And so with the machine learning, you essentially are creating a custom model, and you don't need to worry, about this kind of thing. So let's look at an example of a decision tree that's really based on a more closer to kind of a manufacturing problem. This is kind of theoretical, but let's say the problem here is that you've got an automobile paint process, lots and lots of different process steps, right? You're coating, you're rinsing, you're baking, you're applying paint, you're applying base coats, you're applying clear coats. Every one of those process steps is going to have different pieces of equipment, and there may be sensors on them, a lot of measured data coming out of the process at each one of those steps. So there's potentially a lot of data that can come from a process like this. And for example, we've got an issue here. The clear coat is peeling from cars, and so that is the defined problem that you want to solve. We're going to start out here with this decision tree. The bad product is indicated on this histogram by the blue bars, and the green is the good product. The decision tree, the algorithm determines that maybe the most predictive variable here is the clear coat bake temperature. And so if you have a high clear coat bake temperature, you can see we have a high proportion of good product. If we have a lower clear coat bake temperature, well, that's kind of a mixed bag, right? We've got some good and some bad. As we kind of continue down the tree here, we're looking at other kind of important variables. On the right-hand side, the base coat thickness also seems to be very significant. So high base coat thickness, again, a high proportion of good product, and we can kind of see down here, we have a note at the end that's almost completely good product or good results. And then as we move down the left-hand side here, we've got the different standing stations, and it turns out standing station 3 seems to be a lot worse than standing stations 1, 2, and 4. We've got a lot of bad product. We're still with 1, 2, and 4. We've still got a mixture of good and bad, and so we might want to continue this tree. But this just gives you an example of the kinds of things that you can put into a decision tree. At this type of level, note that we've got continuous parameters here, temperatures. We also have categorical parameters here, the different standing stations or different equipment. And so we can kind of throw all this in and essentially have the algorithm try to tell us what does it take to make good stuff and what does it take to make bad stuff. So if we were then to kind of continue this process, we might end up with a very complex tree, which is shown here. We have many, many different levels. Once we've generated that tree, if it perfectly fits the data that we've used to create the tree, what we see down here is this training accuracy, which is 100%. That just means that we created a tree that perfectly explains all the data that we use to create it. Now, the methodology here is usually to then take another set of data and test the tree. You know, maybe you're going to hold out a portion of your original data or get another sample of data, and then you will essentially drop, that data down this tree and see, which path it follows, and the tree will then predict that, for this instance it was good, or you're going to get bad results. And we can see in this case the accuracy here is not quite as good. It's pretty good, and so we can see that where we are expecting to see good material, that the model predicted some small percentage of bad stuff, and similarly where we expect to see bad material, there's a prediction of some percentage of good stuff. So this kind of defines this concept of kind of training these models with one set of data, but then testing them to determine how good they are with a second set of data. And we'll see that in the demo, how that's used. So to add just a little more complexity here, it turns out that these these single decision trees that are very, very complex have some issues with them, and we actually get better results if what we do is we take a large number of kind of smaller, simpler trees and then kind of average them all together. And so we're still looking at decision trees here, but these are called ensemble trees, multiple decision trees. And the most commonly used algorithms there are going to be random forest and the gradient boosting machine. And the example I have later is gradient boosting machine, and I think Kai may have some random forest in his. So the method here is just to average a large number of simple trees. You basically take a sample of the data, you fit a simple tree, then you look to see how good that tree fits another set of data. You find observations that were not fitted very well, and you prioritize those, and you create a second tree. And then you continue doing it. So it's this process of continually kind of making simple trees, looking to see how good they fit a random data set, finding some groups of observations that it does not fit very well, and then going ahead and creating a new model to try to fit those, those outliers better. And what you end up with then is a large number of trees. You can kind of get the average result of all of them. It turns out kind of empirically that you end up with a better fit and better prediction with these algorithms. So if we kind of look at this gradient boosting machine, this ensemble tree method, and we look at the, some of the result, the types of results and use cases here, we find that this type of algorithm combined with big data sets, it can produce models that very accurately fit fairly complex data patterns. This picture on the right is kind of an illustration of that. If you look at the green line, this might be kind of a classical kind of regression analysis, not machine learning, and it's going to kind of do essentially a best fit, it's essentially a data smoothing technique. But it may miss a lot of the nuances in the data. If you look at these isobars, which is what you would see kind of on a contour map, you can see that in fact the data is much more kind of granular. Maybe you can fit this curve to that type of data, but you're missing a lot of the nuance. You're missing a lot of the granularity in the data. And so the machine learning algorithm then would allow us to get results that look more like these isobar contour lines than the green regression line. So this type of an algorithm is really, really good for data mining and also for predictions, and it works very, very well for complex processes and products. And you'll see, we can look at hundreds or thousands or even tens of thousands of predictors. Those predictors might be sensors or measurements, that are done in process. The algorithm does a very, very good job at variable reduction, so you may start out with tens of thousands of predictors, but, you know, in the end, you'll find out that it's these top 5 or 10 which are going to be the most significant for predictions. The relationships between the response, something like yield or failure, and the predictors can be very, very nonlinear, and there can be interactions between them. And like I said, this scales to big data. So again, it makes it very easy to use. You don't have to specify a data model like you would with classical statistics. We can accommodate both continuous and categorical predictors and responses. The algorithm is not especially sensitive to missing data and outliers, so you can leave those in the model if you'd like, and that won't really skew the results. And all of this you'll see in the demo that we have. It can be kind of packaged up in a very kind of simple, easy to use user interface. So some of the tools we're using, I'm not going to go into these. I mean, again, that could be that could be really another talk. You know, some of the details of the technology that's working behind the scenes, but we rely heavily on R, the R language, and we have our own version of R in TIBCO, which is called TAIR, which is it's essentially an enterprise version of R, and in many cases we'll get much better performance that way. In R, there are a large number of kind of open source packages available. I think there's thousands, over 8,000 now, and so you have available, you know, very, very easy to find a package that would you know, cover almost any type of use case. We're relying on Spark behind the scenes. That's kind of a big data platform. H2O is something that works with Spark and in our case Spotfire, but it allows us to essentially kind of, you know, it creates some machine learning algorithms, and in some cases that may be kind of in data source instead of running those things, you know, locally on your machine, and so you have potentially, you know, you can work with much bigger data sets. So quickly, almost done with this section, but if we shift to manufacturing here, we know in a manufacturing process we have lots of different types of data. We have data coming from suppliers, you know, incoming materials and components, lots of different types of data from the manufacturing process itself, information on product quality and reliability testing, and then we may even have some field returns. So the problem that we're going to define, you know, is essentially going to take one of these, you know, types of data as the response, and other data is you know, trying to predict based on that. So for example, product quality is often looking at kind of measured product functional characteristics or performance characteristics, and trying to see if we can look at some of the information from the manufacturing process might be used to predict that. If we're looking at predictive maintenance, we're going to be maybe looking more at kind of equipment maintenance information, you know, when did the machine go down, and maybe we can then predict based on some of the sensor data, you know, when we should take machine down for equipment. So there's a large number of possibilities here, you know, looking at predicting either what's going to happen on a product, what's going to happen with an individual process, or what's going to happen with specific pieces of equipment based on other data that we have. So if we look at kind of the use case here, like we said, we want to kind of predict product and equipment problems. Those can be very, very difficult to diagnose, you know, when you have complex manufacturing processes. This may be a big data problem. We might have millions of manufactured units. We might have hundreds or thousands of predictors. Those predictors are things like measurements that are done in the process. Some of that's going to come from sensors, Internet of Things type of stuff. So we want to be able to accurately model that type of stuff. We have a fair amount of experience now working with customers, and customers, you know, are finding previously undetected problems with this technology. So it's very exciting.
I'll tell you now in 2 slides before we come to our 2 live demos, is that you explain you the idea of what we are doing actually with these machine learning kind of development paradigms. So it's really, as you can see here, an insight action loop, and that means we combine 2 things. First, we have to understand the historical data and find insights in that. So we take a look at the big data sets and find insights and patterns in that. And afterwards, we put that and bring that together with algorithms of machine learning to build the analytic model. And then we reuse this model without redeveloping and deploy that to real-time processing. And then we can apply the model there for future events. And that's what you do then for predictive maintenance and all these kind of use cases. So that's the basic idea behind that, and that's also the focus on our 2 live demos, which we will show you. And let's go to the next slide. So here, 1 slide about the architecture so that you understand the components a little bit more. Here it's important that you see 2 different colors. You see the purple and the blue components, and that's actually what I just said on the former slide. So the purple one, that's really about data mining, about analytics and finding insights and patterns and historical data. For that, you use any kind of data storage. So, for example, in these use cases, we use a big data store like Hadoop. And then we use a visual analytics tool like TIBCO Spotfire to do data discovery to find these insights. And if necessary, like here in our use cases today, we leverage the data scientist who built analytic models. So he uses Spotfire or an analytics tool together with these machine learning frameworks like R and H2O and Spark, and he builds the analytic model. And afterwards, and that's what you can see on the top in blue, then we deploy the same analytic model which the data scientist has built. We deploy that to real-time processing so that we can act on new events, which you can see on the left, like in this case, sensor data or transactions. And for each single new event in real time, we apply the analytic model in our event processing engine. And then this loop closes again, so of course you have to improve that analytic model all the time, and therefore you review it again with the historical and with the visual analytics, and you can deploy a new model to the real-time event processing. So that's basically the idea behind what we are doing with our use cases. And now we have prepared 2 different scenarios, different use cases, where Mike will show the first demo where we will focus on data mining and historical analytics of data, and I, in the second use case, will focus on putting that analytic model into real-time processing.
Okay, thanks, Kai. Yeah, so I'm going to do a Spotfire demo that focuses on data mining. People sometimes call this root cause analysis. It may not actually get to the real root cause, but we are what we're doing is we're looking for variables that will essentially allow us to predict some kind of an event. In this case, usually some kind of an equipment type of failure. So quickly, if we look at this particular use case, we're trying to understand the causes of yield loss in a manufacturing process. Basically, it's looking at, you know, percent product that are failing. So our response, our output is going to be, you know, individual units that either pass or fail. We've collected a data set with that information. And then the inputs or predictors are around 600 different equipment sensor and in-process product measurements. And we have that information for each particular unit. So if we look at the configuration screen here, we basically need to, you can see we have a large number of predictors or columns in this data set. You can see we've got hundreds and hundreds of them here. And we basically want to kind of tag each each column of data as either the response, which in this case is yield loss, and that's just kind of a 0 or 1. You can see that here, either the unit passed or it failed. But then we have a number of other data columns here that are some kind of measurement, either that's a measurement off of a piece of equipment, or, you know, which is a sensor reading, or it could be, you know, some other measurement that we collected in line. And so we have a very simple interface here for defining this. This is kind of, you know, this is real data. There's some anonymization that's taken place here to you know, but these kind of measures might be things like temperatures or pressures or thicknesses or something like that. And so we just kind of mark the things that we want as predictors or responses here, and then we say update it, and that will then tag these things. So pretty simple, easy to use interface there. Once we've done that, you can see I've actually run this, you know, for one result here. On this screen, we're going to do some kind of configuration. So if you remember when I was talking about the decision trees, and actually this is ensemble decision trees, we can define a maximum number of trees that we want to get. This would be to, you know, keep it from running for too long. So in this case, I've set the maximum at 1,595 trees. The interaction depth is just the number of levels in the trees, and we can also say, you know, what's the minimum number of observations in each node. If we have a smaller number of units, you know, in a node there, then we say that that's really not enough to, you know, to utilize. So anyway, there's a number of parameters here that the user can set. This holdout sample size is, remember I talked about training data sets and test data sets. And so this holdout sample size is the size that we're going to reserve for testing later on. And that's a random sample. When we hit calculate, then we get some kind of a result here. So the result should be fairly easy to understand. This graph is showing us actual versus predicted. If this was a perfect model, we would probably have enough, you know, the points all lining up on this red line here. These points look like they're pretty close to it. This one is pretty far off. So that's an indication that we have a model that's okay, but it could be improved. This curve on the bottom is called an ROC curve. We've got true positive readings versus false positives here. What we would like to see is a curve that follows along this green line. So we basically have, you know, no false positives and 100% true positives. This blue line is the actual curve. You can see we don't have exactly that. This red line here essentially represents random chance. So we have a model here that is predicting, you know, better than random chance. There's some value to it. We might want to go ahead and do some things to improve the model, maybe include some additional variables, something like that. So, yeah, and I'll come back in a second and show you a little bit more about this. This then is the result, which I think is pretty easy to understand. You know, you can see we have a large number of predictors here. We have hundreds and hundreds of them. Again, each one of these might represent some kind of a sensor reading, some kind of measurement taken in line, and we're able to then kind of see the effect of each one of those predictors, sensors on, in this case, the yield loss of this process. So you can see here that for this particular one, we do have kind of minimum yield loss in this small area here, but then the yield loss kind of rises, you know, as the value of that measurement gets either lower or higher. So this says we kind of have a restricted process space here. Ideally, you know, you'd want to see that to be flat all the way across. You wouldn't want to see your yield drop off, you know, across the process space. And we can then kind of look at other predictors here and see, you know, what they look like. So, you know, we can kind of quickly go through here and see, you know, see the things that are having the greatest effect on the process. The biggest one is the first one. You can see we're going everywhere from 4.5% up to almost 8% yield loss as we vary this. So this gives you an idea of the kinds of things you might want to look at, you know, quickly and see if there's a way to restrict, you know, or modify the process maybe. The other thing that we've got here is interactions. So we're not just looking at the effect of you know, one thing at a time. If we look at for example, the top interaction here between different sensor readings, we can see that we have kind of maximum yield loss where these two sensor readings are the highest value. We're almost up to 30% yield loss here, and down in, you know, for lower values there, we're essentially at 0. So we want to investigate again here, you know, what's going on where both of these kind of sensors are at their highest value. One thing we could also do, so I mean, I showed you what, you know, that we have the ability to evaluate the models here. We could kind of quickly look and see, well, okay, what happens if I reduce the number of trees, you know, down to 20, you know, maybe reduce the interaction depth here. I could rerun this model. We could see what it would give us and watch these kind of two curves on the right-hand side. You see this curve now is closer to the random chance one a little bit, but really our actuals versus predictions doesn't look very good at all. So again, you know, this is a small number of trees, and it really looks like we would, you know, we did need that other model that we started out with. One other kind of quick comment before I turn it over to Kai here is that what we've been looking at here is essentially all continuous kind of, you know, measurement data for our predictors. We can, with this mix, kind of continuous and categorical. So, for example, here with this interaction, we've got some kind of measured parameter here, but this is categorical. So this might actually be different pieces of equipment. So we can mix them all together, you know, in this model and see what the effects are. For example, these machines here, the first one and the third one, look like we're seeing kind of a relatively high amount of yield loss, you know, for high values of this sensor. But we have other machines here that seem like they're completely insensitive, you know, to the value, to the readings that we're getting on that sensor. So this is the kind of, you know, thing we can do when we're looking at categorical and continuous together in the same model. So with that, I'm done with this demo. I'm going to stop sharing and turn it over to Kai, and he'll show you the real-time.
Okay, thanks, Mike. Let's double check. Can you see my slides here again?
Yes.
Okay, great. Okay, so what Mike discussed is really the data mining, data discovery part where you find insights and create analytic models. And I now want to focus on the second step, because these analytic models, of course, only help if you then can apply them afterwards to some kind of event, to do something with it, to get business value out of it afterwards. And therefore, what I want to show you is another use case, so that you see also different use cases here. And this is for another customer where we realized a predictive analytics project for manufacturing. And in this use case, it's about assembly lines. And the goal was to scrap parts as early as possible to reduce costs in a manufacturing process. So the question here really is on the screen, as you see, when to scrap a part in station 1 instead of moving it to station 2 or doing rework here in station 1. Here you see the cost. Before it is €9, and then it's €7 in station 1, 13 in station 2, and so at least it is €29. Even if you do rework, it's getting more expensive, of course. And what we want to do here with this process is we want to decide when to scrap parts early. We want to use a machine learning model to do that in real time, and also, of course, automatically, because here we are really talking about thousands and thousands of events, and this cannot be done manually. So the goal is to create an analytic model to do that and deploy that to real-time processing. I have shown you the reference architecture before, and here is really a real-world example of how we did that with some specific technology. In this case, events or XML file, so it's really not a perfect data for real-time processing, but it was absolutely fine for us. And then as data storage here, we had Apache Hadoop, and we had different connectors like Apache Flume and the HDFS, the distributed file system of Hadoop, to connect. And with that big data master of historical data, we first found the insights. And here, our business user and data scientists work together. And in this case, they used H2O as to create an analytic model. And the reason for that was that in this case, they need really a lot of events, so it's thousands of events. And so you have to execute the analytic model in real time quickly. So this was the best technology for this project. And what we can see here now, and that's really the key, we reused the H2O analytic model and deployed that to our real-time engine here. So the same model which the data scientists created was deployed to our stream-based real-time engine to process it for every event here. So for each single new XML or JSON message we get through the sensor, our analytic model is applied here in real time. And that's basically what I want to show you now a little bit. First, I have a few screenshots just to also show you the data discovery process. So this was what the data scientist and the business user did together to get some information about the data they had. And then the data scientist built different analytic models. So that's also what's happening in the real world often. You do not just use one algorithm and to build one analytic model, but you try out different ones. Like here you see we used a random forest algorithm and also a GLM algorithm, which is simply a different machine learning model. And here we see the savings we have, 97,000 per month with this model and 76,000 with this. So we decided to deploy the better model here, of course, because we can save more money with it. And so this was the model which was developed by the data scientists and also used in Spotfire. So here you can see also that the business user also can leverage the model as Mike has demonstrated. So the business user does not have to understand what a random forest model is. He just applies it to his web UI here. So that's the benefit also, how the business user and data scientists work together usually. And then here you can also see, Mike has discussed that, an analytic model is usually not 100% sure because it's just machine learning, it's not 100% sure model. And so it's okay here to have some faulty messages and decisions. But still, it's good enough and saves a lot of money. So even if it makes some wrong decisions, we can deploy it to real time to our assembly lines. And afterwards, of course, we can improve it by analyzing the new data to make these decisions even better in the future. But now, really, we come to the part where I want to also show you the live demo. We want to deploy it to our real-time streaming analytics engine. And this is TIBCO Streammaker in this case. And here first, I just want to show you a few use cases, a few screenshots to show that really this is just one of the visual components of Streambase in the development environment. And here you can see at the bottom that really in this case our model is really without redeveloping it is deployed to our streaming engine. So that on every new event you can apply this analytic model. And the same is true in this case for H2O, where we have an H2O random forest analytic model. That's also the one which I want to show you in the live demo. But you should be aware that we can deploy any other kind of analytic model also and process it in real time. So most of our customers do not just use one technology for building analytic models, but different ones. And in the end, we can deploy all of them to Streambase. That's the important point also to understand. And of course, we also have some kind of live monitoring. So we have TIBCO Live Data Mart, which is also a part of the streaming engine. So this is not a tool for monitoring just historical data, but really for analyzing data in real time. So the information from the sensors is pushed to this live UI in real time, and not just for monitoring, but also for doing action proactively, like changing rules or stopping a machine or sending a mechanic or doing any other kind of actions which you want to do. So this was just on the slide to show you how this works with the data discovery part. But here I want to switch to my live demo, where I can show you how this example is implemented in this project. First, I want to stay in the IDE, in the development environment, for a minute. So here you see that all of this is coded visually. So you do not write source code, but you just drag and drop the different components or filtering and aggregations and transformations. So this is one part of streaming analytics, but what I want to focus on is really here the analytic model part. So one of these components in this more complex process where we analyze data, we filter it, we parse the XML data, and then one component here is the H2O component, so that we simply here apply our H2O model. Here you see this is H2O generates a Java file, so, and this compiles to Java bytecode, which is then executed with every new event which comes into this via a sensor. So at this step, we apply our analytic model, and this is now done for every single event. And therefore, let me go to the UI. In Live Data Mart, we have two UIs. We can either use a rich client, which is a desktop application, or what most customers in the meantime want to do is they want to use a web application. So here you can use that on your web browser, but also on your mobile device, of course. And by the way, the same is of course also available as API, so that you can also build your custom applications with that. Here, let's take a look. I have run that before our WebEx today, so I'm in Germany, so here it's already 5:30 and now 6:30. So this is some events which happened, and for each single event, you can see here that the analytic model was applied to that. And all of the blue ones that you can see, these ones are okay. So it was decided in the station 1 not to rework it, but to move it to station 2. On the other side, you see here predictions which are higher than 0.5. In this case, it was configured that everything over 0.5 in this analytic model is scrapped. So you see here the events which were scrapped, and all the blue ones were moved to the next station. So again, this is probability with our analytic model, and of course you can also change the rules here so that you only scrap everything over 0.9, for example. That's how it depends and makes sense in a use case. And what's also important here is the second screenshot here, or the second, not screenshot of course, but the second diagram here, where you see the execution time. And that's also important, especially for manufacturing, where you usually have a lot of events, where you have thousands of events or even millions of events. And if you take a look at the execution time here, for the complete streaming analytics process, it takes an average, as you can see here, 8 milliseconds in this case here, or here 5 milliseconds. So that's the complete process which we execute here in our streaming engine. And that's really important that you can quickly execute the complete process, including the parsing, the filtering, the transformation, and then also the applying the analytic model. So applying the analytic model here is less than a millisecond, right, with H2O. That was one of the reasons why H2O was chosen here. And with that, you can imagine that you can really do that for Internet of Things and predictive analytics in assembly lines and everywhere, even if you have a lot of different sensors. So let me just go here to the test and debug mode, because this application is already running. And I stopped it to show you the live UI in a stop mode, but I now will resume the application, and that's also nice because you can here really use this kind of feed simulation to try out how it would work later in the live systems. And now if we go back to that, you can see here it's updated in real time, because here on the left side you see it was 5:30 at my local time, and now we are seeing data from 6:30 on the right. So this takes a little bit of time. Let's make this even faster so that we can progress a little bit more quickly. And now you see here in real time how it updates the information on the right. And here again you see we have a lot of new scores of new events. Most of them are moved to the next station, but a few of them are scrapped because the analytic model had a score here which was over 0.5. And the same is here now true for the execution time. So you see here, it's always, even in total, it's an average of less than 5 milliseconds. And just executing the analytic model, as you see here, has an average of 0.34 milliseconds. So that's really what we call real-time processing, and that really fits into stories for manufacturing, especially with many devices, with many sensors, and these kind of things. And that's what I wanted to show you here in the live demo. And with that, let's finish this up with a few more comments about our community. Mike, I think you can take over, and then we can take to Q&A.
Yeah, so if you're interested in, learning more about this and actually doing more with it, I just want to make sure everyone knows, I mean, we have kind of a TIBCO community site. It's been relatively recently, a lot of effort has been put into it. So there is a wiki page there now. You can see the URL down at the bottom that focuses on machine learning, where we've tried to pull together all of the assets and links to, all of the relevant information on machine learning. And then we have a component exchange, and the idea of the component exchange is that we'll provide data functions, Spotfire templates, and accelerators that will allow you to do some of the things that we've been showing you just by downloading some of those components, and you can begin to work with them immediately. So with that, I think I'll throw it open for questions if anyone has any. And probably the best thing to do with questions is, if you have some, is to put them in the Q&A window, and we will try to answer.
Okay, we do not have any questions yet, so while you might still typing them in, one more important information maybe for you, what we did not show in this presentation is that we also have what we call a TIBCO accelerator for industrial equipment. So TIBCO has a few accelerators that's really open source projects also in our community, and you can download them and apply them to your projects. And there we have a lot of templates which are really built exactly for these use cases of sensor analytics and machine learning and so on. And that's just another information. And now I see one question here. So the question is, there was a mention earlier about forests not being sensitive to missing data. Could you elaborate on how Spotfire forests handle missing continuous data? And I think, Mike, that's a question for you.
So I think the answer to that, really has to do with, how these decision trees work. And what the decision tree, attempts to do is to find, for example, if it's going to split continuous data, there may initially be a split, somewhere in the middle of a continuous data range. But as you continue down that tree, if there's an outlier, it will essentially segregate, outliers and missing data. Well, I'm sorry, it's going to segregate outliers off into kind of its own branch. And with missing data, the algorithm essentially is going to, it's going to ignore those data points. So if there is missing data, a whole record will not be used in that case. Now there would be ways to probably do some interpolation, which would try to fill in kind of missing values. That would be an extension, kind of a pre-processing step that could be done.
Okay, the question is also answered, so thanks for the feedback. And we do not see any other questions, so we hope you enjoyed this online meetup, and we are happy to get questions from you afterwards, also via email or on our community. And definitely we will do more of these kind of WebExes and online meetups, so hope to see you soon. Thanks a lot, and if you have any questions afterwards, come back to us. Thanks, and Goodbye from my side.